4 astronauts are scheduled to fly farther from Earth than any humans in history, but their spacecraft nearly never made it off the drawing board. After spending $55 billion in decades of development, NASA's Artemis II mission faced a cascade of failures that threatened to ground the program permanently. The most serious new problems weren't discovered in design reviews or computer simulations. They were found when pieces of the heat shield started falling off in space. What followed was a 2-year race against time to solve problems that had never been seen before, using fixes that had never been tested at the extremes of lunar return. Artemis II represents NASA's first crewed lunar mission since Apollo 17, carrying Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen on a 10-day journey around the Moon. The mission will take the crew 695,000 miles from launch to splashdown, passing within 4,000 miles of the lunar surface and reaching 253,000 miles from Earth, farther than any human has traveled before. Their trajectory will trace a figure 8 around the Moon, testing every system aboard the Orion spacecraft in the harsh environment of deep space. But the uncrewed test flight that preceded it, Artemis I, revealed what NASA's Inspector General called critical issues that could have killed the crew. Multiple investigations found problems with the heat shield, life support systems, electrical power, and even the launch tower itself. The mission survived only because NASA made a controversial decision: accept risks that previous generations of engineers might have considered unacceptable. The agency was about to bet 4 human lives on solutions that couldn't be fully proven until the moment they were needed most. Artemis I's Orion capsule returned from its lunar voyage in December 2022 with a 16.5-foot heat shield that looked like it had been attacked with a sledgehammer. Post-flight inspections revealed ablative material had chipped and broken off in more than 100 locations, creating a debris trail instead of the smooth erosion engineers expected. The damage pattern defied every computer model and ground test that had validated the design. Chunks of Avcoat material had separated from the shield's surface and tumbled away into space, with imagery showing multiple pieces of charred material shedding and briefly clinging to Orion's windows during re-entry. The Avcoat heat shield is the largest ever built for a crewed spacecraft, designed to withstand 5,000-degree plasma during 25,000-mile-per-hour re-entry from lunar distance. Each honeycomb-shaped block of ablative material was hand-fitted and cured in place, creating a mosaic of protection that had to work perfectly or risk catastrophic failure. NASA's Inspector General warned the unexpected char loss created meaningful risk that the heat shield might not adequately protect internal structures on a crewed mission, and that liberated fragments could damage the capsule exterior and compromise parachute deployment. The falling debris could strike Orion's windows, antennas, or reaction control thrusters, crippling the spacecraft's ability to navigate or communicate during the most critical phase of flight. A dedicated Tiger team of specialists spent more than 2 years trying to replicate the failure in ground tests but could not fully reproduce the exact material response in flight environment. The investigation involved more than 100 tests at specialized facilities, including arc jet runs, before NASA identified the root cause in December 2024. Gases generated inside the Avcoat during ablation could not vent as expected, leading to internal pressure buildup and uneven shedding. The Avcoat was basically cooking itself from the inside, creating gas pockets that exploded outward when pressure exceeded the material's structural limits. The problem was made worse by Artemis I's skip re-entry profile. 2 dips into the atmosphere separated by a brief climb, which allowed thermal energy to accumulate inside the Avcoat while heating rates decreased between skips. Like a sponge soaking up heat, the material absorbed energy during the first atmospheric pass but couldn't release it fast enough during the cooling period that followed. NASA faced a choice: completely redesign the heat shield, which would delay the mission for years, or change the re-entry trajectory to reduce gas buildup conditions. The agency chose the trajectory change, switching Artemis II to a more direct entry path that subjects the crew to higher peak deceleration and sharper heating in exchange for a simpler thermal profile. The new trajectory would slam the crew through Earth's atmosphere like a meteorite, trading the gentler skip entry for a more brutal but predictable thermal environment. Independent aerospace experts noted this trade-off is reasonable but still depends on models that cannot be fully validated on the ground, meaning the heat shield remained the single most consequential uncertainty facing launch. Ground testing cannot perfectly simulate Orion's high-speed lunar return environment, especially the complex thermal and mechanical interaction between Avcoat blocks, underlying structure, and re-entry flight dynamics. Engineers had to extrapolate from limited data, knowing that their predictions would only be proven right or wrong when 4 human lives depended on them. The heat shield investigation had consumed 2 years and tens of millions of dollars, yet still left NASA with mathematical models rather than absolute certainty. While engineers focused on the heat shield surface, Artemis I revealed a potentially catastrophic hidden problem lurking just beneath. 3 of the 4 bolts holding the crew capsule to the service module had melted beyond their design limits. These separation bolts must be pyrotechnically severed just before re-entry and are surrounded by Avcoat blocks designed to keep them flush with the protective material. The bolts represent a single point of failure. If they don't separate cleanly, the service module remains attached to the crew capsule during re-entry, creating a tumbling, uncontrollable mass that would kill everyone aboard. Post-flight analysis found that erosion and exposed gaps allowed hot gases to penetrate into the bolt interior, exceeding thermal limits by margins that NASA's original models said were impossible. The superheated plasma had found pathways through the heat shield that no computer simulation had predicted. If melting had penetrated beyond the thermal barrier, hot gas could have been ingested behind the heat shield, risking structural failure of the entire capsule, an outcome that would be instantly fatal for any crew aboard. NASA implemented what it called minor hardware changes, adding extra thermal barrier material in the bolt gaps, but the fix remained coupled to the heat shield problem until both issues could be resolved together. The separation bolt investigation revealed how much NASA's pre-flight models had underestimated the harsh realities of lunar return. Engineers were learning that the extreme environment of high-speed re-entry created failure modes that simply didn't exist in ground testing. During the same period, Orion's electrical system experienced 24 instances where circuit breakers opened without any commanded action, traced to radiation effects in deep space that ground testing had not predicted. The spacecraft was basically being bombarded by cosmic radiation and solar particles that Earth's magnetic field normally deflects, causing electronic components to behave in ways that laboratory testing had never revealed. NASA's investigation concluded that the power conditioning and distribution units could experience further anomalies that might lead to loss of redundancy, inadequate power, and potential loss of vehicle propulsion and pressurization. Rather than redesign the hardware, which would require invasive rework inside an already assembled spacecraft, NASA chose to accept the residual risk and rely on software protections and crew training. The decision represented a clear divergence between NASA's risk tolerance and the more conservative stance of its independent watchdogs. NASA's Office of Inspector General warned that without permanent hardware redesigns, there remained increased risk that further power distribution anomalies could lead to a loss of redundancy, inadequate power, and potential loss of vehicle propulsion and pressurization. The agency was basically betting that operational workarounds could compensate for hardware that had already failed in ways nobody anticipated. Engineers would have to trust that software patches and crew procedures could overcome fundamental design limitations that had been exposed by the unforgiving environment of deep space. Late-stage testing in 2023 and 2024 uncovered additional life support problems, including a circuitry defect that could impair Orion's ability to scrub carbon dioxide from the cabin, a life-threatening failure mode on a multi-day mission. Without functioning carbon dioxide removal, the crew would slowly suffocate in their own exhaled breath, a scenario that had killed Apollo 13's crew if not for their improvised lithium hydroxide canisters. High-voltage crew module batteries showed they might not reliably deliver power through landing under the extreme mechanical loads of a worst-case ascent abort, jeopardizing the abort system's ability to bring crew home alive. These discoveries required hardware modifications in difficult-to-access locations inside the already assembled crew module, work that NASA's Inspector General characterized as schedule-critical and incomplete as of May 2024. Artemis I's launch hit NASA's ground infrastructure so hard that the Mobile launcher tower suffered more than $26 million in damage, roughly 5 times the $5 million originally budgeted for post-launch refurbishment. The Space Launch System's 4 RS-25 core stage engines and twin solid rocket boosters unleashed an acoustic assault that damaged elevators, electrical equipment, enclosure panel doors, and pneumatic tubing on the Mobile launcher, exceeding what engineers had predicted. The acoustic and vibrational environment damaged elevators, electrical equipment, enclosure doors, and pneumatic tubing on the massive tower used to assemble, roll out, and launch the Space Launch System. Elevator cables snapped under the vibration, electrical conduits were ripped from their mountings, and blast doors designed to protect sensitive equipment were warped beyond repair. NASA discovered that its blast deflection and protection systems were inadequate for the most powerful rocket the agency had ever successfully flown, requiring extensive redesigns before Artemis II could use the same launch pad. The flame trench beneath the rocket had been scoured by exhaust that drove flame deflector temperatures to more than 2,000 degrees Fahrenheit, while the water deluge system that was supposed to suppress acoustic energy did not fully prevent unexpected damage. The repairs had to be completed, revalidated, and integrated into launch operations while the clock was already running on limited life components stacked for the crewed mission. NASA faced the risk of premature stacking. Solid rocket boosters and other hardware have finite allowable time assembled and fueled on the pad, so beginning integration before resolving upstream issues could force costly destacking and refurbishment. The Space Launch System's solid rocket boosters contain over 3 million pounds of propellant that begins aging the moment they're stacked, creating an inexorable countdown that compounds every delay. Unlike liquid-fueled rockets that can be drained and refueled, solid rocket motors are basically giant firecrackers that cannot be turned off once ignited. Their propellant chemistry changes over time, affecting performance in ways that could jeopardize crew safety if the motors sit too long on the pad. NASA was racing against chemistry itself, trying to complete repairs and testing before the rocket's own components became unreliable. Communications problems added another layer of complexity when Orion experienced an in-flight loss of contact attributable to hardware and process issues in NASA's Deep Space Network. The global antenna system that provides tracking and telemetry for missions beyond Earth orbit was already oversubscribed, with demand exceeding capacity by up to 40% at peak times. NASA's Inspector General warned that Deep Space Network antennas suffer from aging hardware, maintenance backlogs, and scheduling constraints that have suffered nearly 5 years of delays and significant cost growth. Some of the massive dish antennas were built in the 1960s and were showing their age, with mechanical failures and electronic obsolescence creating gaps in coverage just when Artemis needed them most. For Artemis II, this created a conflict. The network must support continuous high-priority communications with a crewed Orion in deep space, while serving dozens of robotic missions and observatories that also depend on the same antennas. The infrastructure problems illustrated how Artemis II sat at the center of a web of dependencies, any one of which could cascade into mission failure. NASA's solution involved parallel tracks of hardware fixes, operational workarounds, and schedule adjustments that had to be perfectly coordinated across multiple centers and contractors. The agency was basically rebuilding critical systems while the mission timeline continued to compress, creating what investigators described as a critical path where any single failure could trigger indefinite delays. Mobile Launcher 1 represents a single point of failure for the entire Artemis program. If the tower cannot safely support SLS launches, there is no backup facility capable of handling the rocket's massive size and acoustic output. By the time NASA announced Artemis II was ready to fly, the agency had spent more than $55 billion on the Space Launch System, Orion spacecraft, and ground systems alone, with the broader Artemis campaign heading toward $93 billion by 2025. Each of the first 4 Artemis missions will cost at least $4.2 billion to launch, not counting $42 billion in prior development, making this one of the most expensive human spaceflight programs in history. To put this in perspective, the entire Apollo program cost on the order of $250 billion to roughly $300 billion in today's money to land 12 astronauts on the Moon. Artemis was approaching that same cost just to prove that the basic systems could safely carry crew to lunar orbit and back. The U.S. Government Accountability Office criticized the agency for lacking mission-level schedule management guidance and for not performing a formal schedule risk analysis for Artemis missions such as Artemis II, warning that these gaps increase the chance of further delays and cost growth. The original November 2024 launch date slipped to September 2025, then to April 2026, as each investigation uncovered new issues that required hardware changes, testing, and revalidation. NASA's Inspector General explicitly warned that the pattern of delays and cost growth could threaten crew safety if schedule pressure forced the agency to accept risks that proper engineering would normally reject. The agency was caught between political demands for visible progress and engineering realities that couldn't be rushed or ignored. The decision to fly Artemis II represented a shift in NASA's risk philosophy, accepting uncertainties that could not be fully retired before flight and layering redundancy, trajectory choices, and procedural mitigations on top of hardware fixes. This approach differed from Apollo-era practices, where missions were often delayed or reconfigured until engineers judged they had sufficient confidence in major systems, even as they worked under intense political pressure to meet President Kennedy's end-of-decade deadline. The Apollo program benefited from far larger relative budgets and a strong mandate to succeed, whereas Artemis operates under modern congressional budget cycles and international partnership commitments that create pressure to demonstrate progress. Every delay risked political support and threatened international agreements with partners who had committed their own resources to the lunar program. NASA and its independent overseers reached different comfort levels about acceptable risk in several areas, with watchdogs consistently recommending more conservative approaches than the agency ultimately adopted. The heat shield investigation concluded that ground testing could never perfectly reproduce Orion's high-speed lunar return environment, meaning predictions of thermal behavior would always rely on extrapolated models. NASA's December 2024 decision to proceed was based on the judgment that Avcoat gas venting explanations and trajectory changes were sufficient to demonstrate safety, even though modeling uncertainties remained. The agency was basically flying on the strength of mathematical models and engineering judgment rather than the kind of full testing that had characterized previous human spaceflight programs. The choice reflected broader pressures on the Artemis program, political expectations for visible progress, international partnership commitments, and competition with other nations' lunar ambitions. China's rapid advancement in lunar exploration and Russia's renewed interest in deep space missions created a geopolitical backdrop where delays carried strategic as well as technical consequences. Artemis II ultimately launched only after NASA explicitly acknowledged that some risks could not be eliminated, and committed to managing them through operational means rather than perfect engineering solutions. The agency had moved from a philosophy of eliminating risk to one of managing it, accepting that the complexity of modern spaceflight made perfect certainty impossible. Artemis II nearly failed before launch because it sat at the intersection of technical problems that could destroy the crew capsule, infrastructure damage that exceeded all predictions, and budget pressures that left almost no room for error. The mission survived through a combination of engineering fixes, operational workarounds, and a willingness to accept risks that previous generations might have found unacceptable. NASA's decision to fly represented a calculated gamble that layered mitigations and procedural safeguards could compensate for uncertainties that ground testing could never fully resolve. The agency had learned that the extreme environment of lunar return created failure modes that simply couldn't be predicted from Earth-based testing, forcing engineers to extrapolate from incomplete data and trust in redundancy rather than certainty. The crew of Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen will carry with them not just the hopes of a new generation of lunar exploration, but also the consequences of every trade-off and compromise that brought their spacecraft to the launch pad. Their journey will test whether NASA's risk philosophy was vindicated or whether the agency pushed too hard against the boundaries of what engineering can guarantee. When pieces of heat shield started falling off in space, they nearly ended humanity's return to the moon before it began, but they also forced NASA to confront the true cost of reaching beyond Earth's protective embrace. The 4 astronauts who finally lift off aboard Artemis II will be test pilots in the truest sense, flying a spacecraft that has been rebuilt, redesigned and re-engineered based on failures that no one saw coming. Their mission will ultimately prove whether NASA's faith in operational solutions and engineering judgment can substitute for the kind of exhaustive testing that time and money no longer permit.